Good afternoon, everybody. So let us start our lecture today. And today is October 7th, and it's coming up. And today we will cover and complete red-black tree. Okay, so give me 1 second, please. It's opening. Takes time initially. So in our last lecture, we discussed red-black tree insertion. So insertion needs some rotation and then recoloring, right? Okay. So you remember that. First of all, let us recall quickly. There are 5 properties for red-black tree, and I saw that some books and some videos they say 3 properties. They concise this all 5 properties as 3 properties, but it covers everything. So the someone is red. They put 1 and 2 together, okay, and so in some books they did not say the leaf is always nil or black. This is by default, they think, okay. But in the fourth property, what is the fourth property? We discussed that if a node is red, then both of its children are black, right? And you see that. Why it does not start? Okay, you got it. It was muted. Sorry. Okay. The fourth property, if a node is red, then both children are black. So in other words, so it is on the slide, but I did not highlight it. So in other words, it says in any path from root to leaf, there is no 2 consecutive red nodes. So some books they instead of saying the fourth property like this, they said like this one first. Same thing, okay. That means if a parent is red, then its children cannot be red. Okay. Either of these children, neither can be red. Okay. So in some books I saw that some videos they put in different, like these 5 properties they made as 3 properties. So whatever you say, this is okay, but as long as it covers all, then fine. Okay. But our book, we are following the book that covers, let's say, 5 properties. Okay. And the assignment I asked you to do, take a data set, take a random data set, okay, not from the book, okay, or not from exactly from an website or somewhere, and try to gradually build the red-black tree, and make sure that your data set is large enough so that it covers all cases. For instance, do not do that if very small data set. Do not try with a small data set. That will cover only limited number of cases. Okay, our goal is to understand this as much as you can. Okay, I know that this topic is boring. It is not interested. Actually, I did not find interest in this topic. Actually, honestly, I did not find any application for any programs for red-black tree application. Okay. That may be the reason that I didn't find any interest. If I would try, I could find any application, real application, okay, during my programming or assignment or during my work, that would make me more attention, definitely. So sometime, my father was a teacher. So So sometime my father told us a story, and I many times told this story to my student. What is goal of our, so let's say, learning, and then what is our goal of learning? And why you are spending too much time, too much pressure, right, for learning something, and many times we do not see any application or implication of this stuff, but still we are spending too much time, we are spending money for learning that stuff, right? And what is the outcome?
You get credits for a degree.
After that, what? What else? So there are many people who do not know computing, right? But they are rich and then they are happy. In this life they are successful, right? Is it true? True, right? There are many people, they don't know computing, programming, okay? And they are doing good. But why? What we are doing? So we know too many programming languages, we know too many stuffs, but maybe we are not making that much money. We are not happy, and we have many troubles and problems, right? So what is our goal? But still, why we should, especially for student, why teachers give too much pressure or many pressure to our student? It is true, even if you are a teacher and I was a student, you would do same thing, right? What I'm doing, I'm giving you pressure, you would do something. So what is goal? What is our goal? So to us, to me, the goal is that to just sharpen our brain. Just to sharpen our brain. Right? We are studying too much math. So you see that many math, as my undergraduate was math major. So we did a lot of practice in math problem. Especially statics, dynamics, those courses are very, calculus, are very lengthy. So our goal is just to sharpen our brain, so that sometime whenever you have a bullet, you have a pistol and bullet. If you fire, then it will make the wall hole, right? You make a hole in the wall and you need to pass the wall. But whatever, how about if you push the wall with your thumb? What will happen? Your thumb will be broken, right? Or your hand will be broken. But because it does not have that much pressure or strength. But a bullet has strength that it will pass wall, even sometime concrete wall, right? So the goal is to make your brain sharp, so that even if you do something, wherever you go, if you do politics, okay, if you do business, okay, if you are a computer engineer over here, a computer scientist, whatever you will do, your brain, if your brain is sharp, then you will be successful in your area. It is expected that. Nothing else. And you know that outcome of our learning is that after forgetting everything, whatever the little thing you remember, okay, that is the outcome of our learning, right? So for instance, we learned the 3 rules of Newton's 3 rules, right? We did too many in physics and math. We did too many problems solved, right? We solved many problems related to Newton's formula. But after a few years, what do we remember? A little thing. Only remember there are 3 rules of Newton's. Yeah, every force is opposite. Nothing else. We remember only a few things, right? A little bit. That is the outcome. And the intermediate things and the initial thing, whatever you did and practice, is gone. Okay, I'm sorry that I spent some time. Okay, so this is why my assignment goal is to spend some time. Okay, you can sit together and discuss together, but do not copy exactly. Do exactly same thing. Okay. Okay, so in our last lecture we discussed insertion. So I am asking you to take a data set large enough that covers all of the cases for insertion algorithms, and also like deletion. Okay, so today we will discuss another difficult thing, is called deletion operation for okay, and then the assignment, please do not take small data set. At least I can assign at least more than 10 elements. At least 10 elements, then it will cover all cases. Okay. And do not take the example that in assignments or book. Okay, in the slides or book. So let us cover deletion operation. So like insertion, so deletion is also whenever you delete a node, okay, it also preserves all rules for a red black tree after deletion, and before deletion it must preserve, and I make sure that, and we need to make sure that after deletion it preserves, it maintains all properties of a BST. Also it is a red black tree, and remember that a red black tree also a BST, minus ST, right? So it should maintain the order that the right child element of value of the right child is always less than the value of the greater than the value of the root, right? And the value of the root is greater than the value of the left child. For all cases, we need to make sure. So, and also we need to make sure that the colors are properly inserted, or sometimes we need to recolor, especially when we saw that for insertion. Whenever we insert an element, we start with making it red, and then gradually, in order to satisfy all properties, we recolor, right? So recolor means if it is red, then we make it black. If it is black, then we make it red. And then for recoloring, we maintain two special formula, that no adjacent, no parent child red relation, red color, okay, and the number of black nodes in wall paths is same. That are the two things. If you maintain, then it's fine. Okay, and root is always black, we know that. Okay, so here, so the deletion algorithm is here. For instance, so it's part of a deletion. For instance, if say T is a tree here, and G is the element or node we want to delete. So this algorithm is written as a method. You know that. For instance, we are passing in the method, we are passing a tree and a node. Node will be passed as a value. So we are discussing with binary search tree with value, numeric numbers 1, 2, 3, 4, 5, 6, 9, 10, like this, right? So this will be, for instance, there is a tree, an existing tree. The value will be maybe 10 or 15 or 30 or 40. Okay, and it says if left of G. Okay, in the book sometimes it has a G dot left. Some books, and sometimes you see the G dot left, and here in pseudocode sometimes you see that in some pseudocode it says left within maybe parenthesis or within square bracket it says G. That means left of G, the left child of G, okay, is nil. That means sometimes it's equal, double equal, nil, or right child equal, should be equal, double equal to nil. Then Y, okay, then Y, the color of Y will be, then Y equal to G. I don't see any example over here. Do you see Y here? Okay. Y actually over here is the sibling of G. Y is the sibling of G. Okay. Let me see if the book has picture so that I can. So here, for instance, we say X, this is Y, for instance, G may be here. This one may be G or this one may be G. Okay. Or either if Y over here, over here G may be this one. Either Y will be parent or sibling adjacent to close node. So insertion, and then deletion. This is still insertion. Okay. See this is delete algorithm. Okay. So mainly my goal will be there are 3 sub algorithms over here. I will give you some clue how to understand what does these two means. There are some. Fixed actually there are 6 cases. What are the other cases? X okay, color spaces. Okay, so let me try it. So we know that a red black tree is a BST. So before we understand the deletion of red black tree, we need to remember the deletion process of BST. Okay, so here, what is meaning that here? So in a BST, for instance, we have a BST like 5 and then 4 and then 7, okay, and then 6 and then for instance 8. Okay, and let us recall how do we delete a node from a BST. Let us consider that this is a BST. I'm not going to red black tree yet. Okay, this is just BST. How do we delete a node like this node? In a BST, this any node, for instance this node 8.
So just forget about red black J's and just
that's BST.
Okay.
Let's recall BST. So we know that for every there is a leaf, right? There is a leaf for every node. If it is not an intermediate node, then there is a leaf. And if it is intermediate node, there is real node, right? So for this one, there's leaves. Okay. And leaf has null value, right? Or nil value. So nil, n for nil, for n for nil. So n for nil and n for nil. This is n for nil or null, whatever you say. Some language says nil, some language says null. So if you want to delete a leaf node like this level, okay, then what you do is just put, we do not delete, actually we said we delink. That means put this value to here. What is this value? Nil. So this is over here. Instead of 8, say nil. Either nil or null, whatever your language says. Okay. Then this value is no longer exist, right? 8 does not exist. For any case, for all cases, for the root level. for the no, sorry, not root level, leaf level. So for instance, if you want to delete 6 or remove 6, then put any null from either right side or left side, both null, right? Take any null from here and then put it over here. Go to the 6th position, and we, in order to delete, we need to do search operation first, starting from 5 root. If we want to delete 8, so we'll say that whether 8 is greater than 5 or less than 5. 8 is greater than 5, right? Then we will go to right side. Right side will be 7. Still 8 is greater than 7, so we will go to the right side. Then we will get, at some point, that exists, then we will get this. Now whatever you do, how do we delete this one? Just put its child with nil value and replace this value. Okay, then it is deleted. Then 8 is no longer exists, right? For same thing for root level for these 6 and 4.
So you just search it and delete it.
Yes, not delete, actually replace the value by nil. Then it's deleted, right?
Okay.
Okay. Now how about if we delete some node that is not leaf level? For instance 6 or 7, for instance 7. If you want to delete this one.
Then you would put the 6 where the 7 was.
Okay. So for instance, we want to delete 7 out here, right? Then what we will do? Then there are two ways. Either we can bring the left child over here to this 7, right? So there are two steps over here. Move the left child 6 value over here, so it will be 6, and then again this one. Then there is 2 6, right? A BST cannot have two same value. Then this one will be replaced by nil. So ultimately that value is gone. Okay, that 7 has gone, right? This is called left predecessor, the left predecessor, and another is called right. There is another way, it is called right predecessor. So if we can, so this is, we are replacing, let me go it back. We are replacing 7 by 6, and there is another way. Instead of 6, you can replace by, it's called right successor. So right successor will be the lowest value in the right side. This is the only value, so 8 is the lowest value on the right side. So you can bring 8 over here. So instead of 7, it will be 8, and then this replace this 8 by nil. So 8 is gone, and then 8 is over here, and still it is a BST, right? So in both cases it is a BST, although the different shape. One way it could be 5. If you take left predecessor, then 5, then it comes 6 after deleting 7, right? Okay, and then 8 over here. This is a BST. Or other way, if you take right predecessor, so this is called left predecessor, and right successor. This is called right successor. Okay, then you will get like this way. Okay, now let us get another example. Does anyone has any question about this? I want to delete this one, remove this one, I will bring another one. Does anyone has any question for this? Simple. Okay, now let us look at another situation. For instance, 5 is here, and then 7, and we got 6, and we got 8. This was the thing, right? We got 9, we got 12. Okay, and then we got 11, we got 15, for instance, like this. Okay, and we want to delete 8. 1 2, remove or delete 8, node 8. So as I said, there are two ways. We can take left predecessor. Okay, so left predecessor means the highest value in the left subtree. So here there is only one subtree, right? Only one. So this is the highest one. Okay, this is left predecessor. So then 9 will go over here. Okay, and 9 will be replaced by is nil there. Okay, and if you follow other ways, so this is called left replacing by left predecessor or replacing by right successor. They call tree successor. Successor means here the immediate greater value or the lowest value from the right side. What is the lowest value from the right side? Lowest, so tree successor means the lowest value from the right subtree. What is the lowest value from the right subtree? No, 11, right? So we get it, this is 11, right? This is 11, and then we put this 11 here, and instead of 8 we put 11 over here, and then 11 it has nil, right? It gets by nil. Nil means is leaf. We are considering everyone has nil, right? Every node has nil, and we are not considering nil. Nil is fine. So then this is called deleting the process through successor, tree successor. That means successor means here on the right side the lowest element from the right subtree, no matter how large the subtree is. For instance, if you want to delete 7, so what is the successor of 7? 9. That's good. Okay, the lowest value from the right subtree. So right subtree here, this entire subtree. Entire subtree. Not here. You understand the right subtree? The lowest value from the right subtree. Oh, different. So this lowest right subtree is the entire part, right? This entire part. And what is the lowest value? No, this is. Oh, sorry. Yes, 8. So we want to move 8 over here. Okay. This 8. Yes, we're gonna move 8 over here. So the move 8 over here. Okay, that's good. So there's yeah, it got 2 pages. That's a good example. We got it. Okay, so 8 will be here. So that is good. 8 will be here, and then 8. There are 2 8s, right? Now we need to remove 8. How can we remove 8? Again, either it's 11, right? It was 11, right? Previously. So you have to move 11. So a right successor of 8 equal to 11, right? So then 11 will go over here. So it will be 11, and then this 11 will be nil. So then in this case it will be. So whenever we are trying to remove 7, so the shape will be completely different, right? So 5 will come over here after deletion. Then 8 came over here, right? 8 came over here, and then 6 is here, and then what is this one? 11. Yes, recursively, yes. There's a while loop.
Okay, the lowest
Lowest value in the right subtree. That is called successor.
Okay.
And you can take the predecessor, that is the highest value from the left tree. You can do it both way, anyway. Let us consider on the book has one way. Yeah, it takes right successor. Right successor is the lowest value. Successor is the lowest value from right subtree. Okay, and the 9 will come over here, and then 11, and then it is 12. So 12 over here, and then 11 is gone, so 15 over here. So this is after.
So the base case of that recursion would be when it's a leaf, right? Because then because if it's like the reason why when we found 8 and then
After
we did
deleting.
the next right subtree is because 8 wasn't a leaf. Is that how it would work?
Give me 1 second. After deleting 7. What is your question? What is your observation?
Okay, so you said it's like a recursive process. So when is the base case? Like when do you stop the recursion? When it's a leaf?
Whenever whenever it reaches to leave.
Okay.
Whenever it reaches to leave with nil value. Okay, understand? How do we delete a node from a BST? Every case you see that it maintains BST, right? 5, all values greater than 5, right? All left values less than 8, 6 less than 8, 11 is greater than 8, but 9 is less than 11 but greater than 8. So it maintains a BST. Okay, now does anyone has any question about this? Okay, so now let us see. So this means that one. So we are moving, so G, that means we are moving G over here. So here, if we say like this is 3, and this is 5, we start with 5, and then we say 7, and we said maybe 4, right? And we said 8, and we said 9 over here, we said 11 something. Oh no, it cannot be 9, it can be 6. Okay. So here, for instance, if you want to delete G, okay, then so then if left child is nil or right child is nil, that means it is the leaf node. Okay, then here it is here, this is G and this is Y value. So then this says Y equal to G. Okay, replace Y by Z, that means this value will go to 6. Okay, and that means until, and then later somewhere it should have this nil. Okay, and then this G by nil. So then this is set. Okay, else, so it should come over here. If it comes over here, then it is easy. It is easy to understand. Give me 1 second, please. Give me 1 second, please. Why is this? What is wrong? It's not moving. Okay, I wanted to move.
Oh, I see. So yeah, that makes more sense.
Yeah. So if you say else over here, right? Okay. Now it makes sense, right? Else Y will be, okay, so then if it is not nil, Okay, that means it is not in the this means if it is in the leaf level, and if it is not in the relief level, right? So then we will do, we have, so for instance, let me say 7 instead of 8 7, let me put it 10, so it's easy to explain, and then 11, make it 16, and then make it maybe 9. Okay, else what do you need to do? We need to do put y value, this value, okay, will be the successor, tree successor of G. Okay, what is the successor of G? That value, the right, if you take the successor of G, it takes the right child, for instance here, the lowest value from the right side. We got a successor, right? This is why. Okay. Okay, so here, so after that, this algorithm, let us go to the, this is from the original BST mode. It does not cover color yet. Okay, now this algorithm is continued, so this is not done yet. That part is that part covers only BST. The main part over here, now it is coming, either you are deleting a black node or a red node. Okay, in a nutshell, let me maybe quickly remember that if you delete a red node, it's easy. If you have a node that is red color, if you want to delete, just delete it. Okay, but deleting, as we saw that deleting a node, it also maintains BST. So if you delete a leaf level red node, just delete it, no question, and easy. Okay, for instance, let us see an example over here that this says I have
Deleting a leaf level red node will never change
no
the
no
violation.
it never change the violation of number of black nodes.
Okay.
Okay, so let us draw something quickly. So something, for instance, it starts with 10 and then 8, I can write it nicely. 10, maybe 6, and maybe 8, and maybe 4, and then 15, and then make us instead of drawing, let me do quickly get the book or examples and explain this, because if I draw, then I have to ensure the color, right? So BST, red black tree, it will take time. Okay, he's already drawn. Okay, I don't like to draw, but I want to explain. Okay, so here, if we want to draw, if you want to, let me get the very special, very simple case. Okay, very simple case over here. If we want to delete a node that is the leaf level and red, for instance this 6C, okay, then delete it, no issue, because you see that if you delete it, so number of black, oh, this is not in right order, this is not a BST, this is not a BST, I'm sorry, I cannot go with this. This is not a BST, this side has 2 and this side has 1. This is not a BST. Let me get an example where I can see delete. Maybe the book has, but we show that I can delete. Case 1, delete. the example, in easy example I'm looking for. The rule is that if you want to delete, this is not EST here. Why do you have a BST? This is a BST. No, this is a red black tree, right? So if you want to delete a node, like for instance 10 over here, if it is red and it is a leaf level, just delete it. Then it does not harm any properties, any other properties. So the number of black nodes same, right? This side, this way, this side, same. Okay, so this is the simplest case. If the node you want to delete, if it is red and if it is in the leaf level, okay, then just delete it, it's not an issue. But now if you want to delete 8, okay, and we see that 8, it has a child, right? And it is not it is what is that called? It is not it's not a leaf node and it is red, right? So then it is still pretty easier than deleting a black node. So deleting a black node, actually it changes the number of black nodes in one way, but it is still, it will be easy. For instance, how do we delete that one? For instance 8. Then follow the BST deletion. What is the BST deletion mode we discussed a few minutes ago? If you want to delete 8, it go to its right subtree. Okay, go to its right subtree. Okay, and get the minimum value, right? The lowest value. What is that? 9, right? Then put 9 over here. So 9 over here. Then in that case, put 9 over here. So 8 is gone. So 8 is gone by 9. No longer 8, right? But now I have again, this one is 9, right? Then I have to consider this one for another case. Okay, and so 9 over here, another 9 over here. So that in that case, how many? 3. How many black? 1, 2, 3. 1, 2, 3. And in that case, it is red. We are not changing the color. We are just replacing the value. First of all,
Red 9.
so red 9 is red. So this is, let me write in red color. So 9 is red. Okay, now we need to delete 8, this 9 over here, right? We need to delete this 9, right? And then this 9, it has if you want to delete a black node, then there are 6 cases. Okay, and remember that whenever we try to insert an element in a red black tree, we also check its uncle's color. Remember that in the last lecture we discussed, whenever we insert a node in a red black tree, we also check its parent color and also its uncle color, right? So here in opposite order, whenever we want to delete a black node, so sorry, this node is black, so let me make it black color. This node, if you want to delete this node, then it need to see its children color, maybe nephew color. So this is why there are 6 cases over here. So okay, so for instance, one thing on we saw one thing that if you want to delete this one, it was easy, right? That was easy, but this one we did, and then what do we need to do right now? Let us see. So from here now we need to delete 9. How can we delete 9? So for instance, if you want to delete 9, for instance, now forget about this part. This part is done. Okay, now this part.
But the 10, well, is the 10 still there, or?
10 is still there.
Okay, so then you just move up the
10, 10.
and then make it black.
Okay. And then 10, yes, 10 will come over here. Okay. And then go to the 10, and 10 is red, right? Now deleting red is easy, right? Just make it null. Okay, we are lucky that in that case.
If you move the 10, why would you need to delete the other 10?
So if you move, still there is a copy over here. We are copying.
So you're just copying the 10. Okay.
So if you have, say for instance, if you have x and y, x equal to 10 and y equal to 5, if you want to swap, how do you do? So then x equal to y, right? If you make x equal to y, then we will imply what? X equal to 5 and still y equal to 5. There is another y, 5, right?
Okay.
You see this? This is why you need to put a temp variable, and you need to put that temp to x to that temporary, and then later for swapping we need to use another temp variable, right? So this is same thing. Still you have this 10 exists, but we don't need to this 10, right? 10 is already in a BST. A value can be only one time. There is no duplication. This is why we need to delete 10. You understand?
Yeah.
Okay, that's good. Okay, so this is the recursive process. Recursive process, it will go down, and for insertion it goes up, right? You check the color for up. Okay, now it covers 2 cases already, 2 or 3 cases. Still we have more cases. Let me see. Let's go.
So deletion is recursively down.
Deletion is going down. It checks the color of down. Okay. Because it takes the element from down to up. Right? Whenever we are taking successor, the elements come from down, right? Okay.
Is that true for all 9 or whatever cases?
No, there are many cases. I'm wondering that I cannot finish in one lecture.
Okay.
Rather than what I want to do, I want to give you some tips, and I found some YouTube videos that are good enough, but an hour long. Whenever you have time, you give concentration, but you do not complete that in one sitting. Do watch half, and then later another time, whenever you have cool brain, to the next half.
Are you going to put this on the D2L?
I will share you. I will put in detail.
Share
I thought I would make a video, but it's no. I could not. So I'm using 4 courses, so it's too much time. Maybe later I will make. Okay. And sometimes not only that, it will need a rotation. And rotation cases are more clumsy. Okay. Now, for instance, this. Now let us think that if case 2, if the node that you want to delete that is black, that is more difficult. For instance, we saw that like one cases, right? But in what happened, think that if there is we discuss with this simple example, right? From here, maybe from here, right? Simple example. But what would happen if we wanted to delete this 6? If it is a black color, okay, then we need to go all the way. So we noted we need to get the successor. Successor will be here is 7, okay, and not only this successor will go 7, it does not mean, because this successor is deleting, right, okay, and then the color, definitely in most cases, you think that in some cases or almost many cases it will make disorder, it will disturb the last property, the number of black nodes. Because whenever you delete this node, middle node, right, black, this is black is one down, right? Okay, and you have to fix all path, for all path, not only on this path. If you have another branches, all branches you need to fix. Okay, then this is case 2. It says whenever you want to delete a node that is black and both children are black, if this case is case 2, if both children are black, for instance, if you want to delete this black node and it has both children, immediate children black, and not about that, it may have more other children, right, grandchildren. But forget about grandchildren for now. For now, think about that. If both children are black, then what do we need to do? C, D, it covers. Okay, move the black. So take Thomas.
All these assume that the red-black trees are already red-black trees.
So these are.
They're like, isn't that not?
No, it is not. It is not red black. Number of 1, 2, and now this is number 1.
Yeah, it's already violating a property. So like, wouldn't the precondition?
So it is the condition. It is, for instance, it is from a branch. It is taking a branch. If you reach in a branch, there is this type condition. So for instance, we saw that from moving, we need to move a child, right, from bottom to up, successor. In that situation, this child, this branch is not required to be red black.
So it's
The
like
entire tree need to be red black. So for instance, that a good question though. For instance, if you take this one, right, okay, so this is the branch, the right side. This is also BST, right?
Yeah.
But it is not guaranteed, it's not required to be a red black tree.
Okay.
If you take this branch, this is a BST, but it's not required to be a red black tree. So the cases that says that branch, okay, that does not require to be a. Then this is BST, this one is BST, but this one is not, middle is not, and the top one also, this one is also BST, but it's not required. Okay. We don't have enough time, so but you see that the algorithm, it says case 1 it is then again apply other cases, case 2, 3, 4, and this is why I told you that it's messed up whenever you go. So in your test, I will not give you that kind of difficult deleting, sure, but I will give you some simple. Okay, maybe not that very simple one, like deleting the red node. Leaf level, but it may be an intermediate level. Okay, you may need 1 or 2 rotations, 2 rotations, few shifting. Okay. Better I will see, I will send you the link of the good algorithm. 2 videos actually I found that. You follow this, okay? And these are the actually, so let us see that for deletion, okay? So for deletion algorithm, since it is a BST, okay, it takes log n iterations, okay, and then the running time complexity is log n for deletion. Even it is go all the way end, no problem, it will be waiting. Because for shifting and then moving, for instance, whenever you are considering for only one branch, right branch or left branch, so it will take log n. Okay, h over here, so in the book it says some h. What is h over here?
Height?
Yes, what is height of a red black tree?
The number of edges from the longest path from the leaf.
Yes, but for a BST, for red black tree, the height balanced, right? What is h over here?
Log 2n?
Yes. Log n, or 2 is implied over here.
Yeah.
Implied over here. Okay. You see that this problem, if you want to delete some, so the color maybe, then if you delete some, so it has problem. This is not a good one. So this is a good one. This is a BST. Red black tree 1 2 1 2 1 2. Okay, I will come. I will share the video to you. But does anyone has any question? Okay. And if I give this problem in assignment, I will give it an assignment because then you have enough time. Okay. In the test, I will give you some with specific figure, and then I will ask you to do something special. Okay. So that in the test, so that I don't like to